If you want to understand risk assessment, and in particular if you want to undertake risk assessment using things like Bayesian networks, then clearly you need to have a basic understanding of probability. And in this video, I'm going to provide this understanding from the laws of probability to Bayes' theorem. It's a fairly gentle introduction to probability, and much of the material here you can find in the 2018 version of the book I wrote with Martin Neal, and you'll find lots of additional material in there. And there's also, I would recommend this website, which has regular updates of the book. There's plenty of exercises and solutions, as well as any corrections. Ultimately, for risk assessment, we're interested in determining the chances of the following kind of events. And you can see there's a very broad type of event here, beyond those which are normally considered in most probability books. So one that you will see will be something like the next coin toss will be a head. That's usually very well covered in probability and statistics textbooks. England will win the next World Cup. That's not something that you'd typically see, but that is trying to predict some future event. Bank X will suffer a loss tomorrow. We're now veering into uncertain events which people associate with kind of like risk assessment. Oliver Cromwell spoke more than 3,000 words on this particular date in 1654. And that's kind of a bit weird, but nevertheless, that's still the kind of event that we want to determine the chance of. O.J. Simpson murdered his ex-wife. You're carrying a virus. In order to properly define probability, we have to introduce the notion of experiments, outcomes, and events. So the act of tossing a coin and observing some outcome of interest, like whether it lands on a head or a tail, can be regarded as an experiment. The possible results of the experiment are called events. So head or tail events of the coin tossing experiment, they might not be the only ones. It could, for example, land on its side, or it could fall down a drain or whatever. It depends on the context. Another classic experiment is rolling a standard six-sided die and just looking at the number which lands on top. Now, events there are 1, 2, 3, 4, 5, 6, and we can consider them as elementary events in the sense that they can't be broken down into kind of like smaller events. But of course, we can also consider other events which are made up of these elementary events, things like an odd number, an even number, or a number greater than 3, etc. But it's important that we distinguish between experiments, outcomes, events, and elementary events. So next coin toss will be a head is an elementary event of the experiment tossing a coin and see which side it lands on. And in general, of course, other elementary outcomes of that experiment, as we've seen, are tail, but it could be neither, where it lands on its edge or gets lost. England will win the next World Cup. We can think of that as an elementary event of the experiment, play the World Cup and observe the winning country. Now, the other elementary outcomes there are each of the participating countries, plus we'd have to add none in the case where the tournament gets cancelled or doesn't go ahead. Bank X will suffer a loss tomorrow. Well, that's an event of the experiment of running Bank X for a day and observing the financial movement. It can be considered as made up of elementary events like fraud loss only, loss transaction only, fraud and transaction losses, other losses, etc. And other events might be profit, other, etc. Oliver Cromwell spoke more than 3,000 words on that particular date. Well, we can think of that as an event of the experiment of Oliver Cromwell living one day, where the outcome of interest is the number of words he speaks. So the elementary outcomes are 0, 1, 2, 3, all the way up to maybe some suitable physical limit on how many words a person can speak in one day. O.J. Simpson murdered his ex-wife. Well, that's an elementary outcome of the experiment of observing the death of O.J. Simpson's ex-wife. The other elementary outcomes are a person other than O.J. Simpson murdered his ex-wife, and O.J. Simpson's wife was not murdered. You're carrying a virus. Well, we can regard that as an elementary outcome, namely virus, of the experiment of running a perfectly accurate diagnostic test, whose other outcome is no virus. Now, the type of events that we've been looking at have been quite diverse, and people think that you can't handle the uncertainty about these in the same way. But that's because people are assuming that uncertain information and incomplete information are somehow completely different, and they're not. So the events next coin toss will be a head, England will win the next World Cup, Bank X will suffer a loss tomorrow, are clearly all uncertain, because they're experiments that have not yet happened. So everyone can agree on that, if you like, they're future events. But then the events like Oliver Cromwell spoke that number of words and O.J. Simpson murdered his ex-wife, they either happened or they didn't. But with the possible exception of O.J. Simpson in the second case, nobody knows with certainty whether they did happen, they didn't. So from an uncertainty perspective, although these events have already happened, they're no different to those above. They took place in the past, but because of our incomplete knowledge about them, they are still uncertain. And then we've got an event like you are carrying a virus. Well, it's definitely either true or false. But unless you've already had a perfectly accurate diagnostic test, there's uncertainty about it. So again, from the uncertainty perspective, there's no different to the events above. So that's an event which is happening now, about which, again, because of incomplete information, there's still uncertainty. The key thing is that the way that we deal with uncertainty in all these cases is going to be the same. Statements which express our uncertainty about any event can always be expressed as a percentage chance that the event did happen for past events, is true for current events, and will happen for future events. The percentage that expresses our uncertainty can never be less than 0. Those are events that certainly cannot happen, or greater than 100. Those are events that certainly happen. And by converting percentage uncertainty into numbers between 0 and 1, just by dividing it by 100, we talk about the probability of an event, which we write as P of the event. Now, the thing about probability is that unless you establish some laws, which are also called axioms, you can't actually prove anything. And these probability laws simply capture intuitive perspectives about expressions of uncertainty. So the first law, which is that the probability of any event is a number between 0 and 1, where 0 means the event is impossible and 1 means the event is certain, just expresses that intuition about the language of uncertainty. How do we determine the probability of an event? Well, as a start, we can assume that if there's a finite set of n elementary events for an experiment, that they're all equally likely. So, for example, for the die roll experiment, there are 6 events, 1, 2, 3, 4, 5, 6, and they're all equally likely for a fair die. And in that case, the probability of each elementary event is, in general, 1 over n, or 1 over 6 for this case. And incidentally, that's also the reason why it seems reasonable to assume that tossing a head on a coin has a probability of a half if the only possible outcomes are head or tail. So as I said, the probability laws are also sometimes referred to as axioms. Probability law 2 says that if 2 events A and B are mutually exclusive, then the probability of either event happening, which we write as the P of A or B, is equal to the probability of A plus the probability of B. Now, first of all, what do we mean by mutually exclusive events? Well, they're mutually exclusive if they cannot both be true at the same time. So if one is true, the other must be false. So, for example, for the rolling a fair die experiment, let A be the event 5, we roll a 5, B be the event, we roll a 6, and C be the event, an odd number. Then A and B are mutually exclusive, because if we roll a 5, we can't also roll a 6 at the same time. And because we know that the probability of A is a 6 and the probability of B is a 6, it follows from this law that the probability of throwing a 5 or a 6 is 1 6 plus a 6, which is a third. Now that's a law, but we can intuitively feel that that is the right answer. Now, since C is the same as the event 1, 3 or 5, that's the odd number, it follows that the probability of C, that's the probability of rolling an odd number, is the probability of 1 plus the probability of 3 plus the probability of 5, which is basically a half. Now note that A, which was the event rolling a 5, and C, rolling an odd number, are not mutually exclusive. Because obviously, if you roll a 5, you're also rolling an odd number. But B, rolling a 6, and C, rolling an odd number, are mutually exclusive. So the probability of rolling a 6 or an odd number is 2/3. The third law says that if E is the event which comprises all of the elementary events for an experiment, then the probability of E is equal to 1. That's effectively saying that probability of an event that is certain is equal to 1. And these certain events are also called an exhaustive event. It's certain to happen because it includes every possible event. So again, for the die roll experiment, the event E is just the event a 1 or 2 or 3 or 4 or 5 or 6. Now once we've got these laws, we can start actually to prove some theorems, what we call these probability theorems. And as an aside here, I should say that if you look at different textbooks on probability, sometimes theorems will be presented as axioms and axioms presented as theorems. They are actually interchangeable, so it depends on what you choose as an axiom and what you choose as a theorem. Because we've chosen those three axioms, we can now prove this as a theorem, that for any event E, the probability of not E, which is called the complement of E, is 1 minus the probability of E. So sometimes that might be presented as an axiom, and then you'd be able to prove as a theorem one of the axioms or laws I've already showed you. So for example, for the Dirac experiment, the probability of not throwing a 6 is just 1 minus the probability of throwing a 6, which is 5/6. Well, how do we prove this theorem? Well, first of all, the events E and not E are mutually exclusive by definition. So by law 2, probability law 2, the probability of E or not E is the probability of E plus the probability of not E. But E or not E is the exhaustive event, it includes every possible elementary event. So by law 3, the probability of E or not E is equal to 1. Well, now, this should be from 1, 2, of course. From 1 and 2, we get the probability of E plus the probability of not E. So the probability of E plus the probability of not E is equal to this, but we know that this is also equal to 1, so we can say that that is equal to 1. If we simply rearrange these to that side, then we get this. So the probability of E is 1 minus the probability of not E. And there's a theorem. We can prove other theorems. For example, so far, we know what probability of A or B is when A and B are mutually exclusive. But if they're not mutually exclusive, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, i.e. the probability that A and B both happen. Now, I'm not going to show you the proof of this. It's on pages 96 to 97 of the book. But there's a problem here anyway, because even given that theorem, what we haven't yet shown is how to calculate the probability of A and B, the probability that both events happen. And it turns out this probability depends on whether A and B are independent, and that means we've got to somehow introduce this notion of independence. And what we're actually going to do is come up with an informal definition of independence. So consider two experiments, one where Jane tosses a fair coin and one where Joe rolls a fair die. Now intuitively, whether Jane gets ahead can't possibly influence whether Joe rolls a 6 and vice versa. And in fact, if you think of it as a joint experiment, which has these 12 equally likely outcomes, this would be Jane tosses ahead and Joe rolls a 1. Again, similarly, Jane tosses ahead, Joe rolls a 2, etc. There's 12 of those, they're each equally likely, so each has got a probability of 1 over 12. And this means that if you take a particular event, like Jane tosses ahead and Joe rolls a 6, then that's going to have probability of 1 over 12. So here we can think of the joint experiment, and what we can see in this case is that that probability of the head and a 6 is equal to the probability of head, which is half, times the probability of getting a 6, which is a 6. So in general, we say that two events that cannot influence each other are independent, and we also observe that the probability of both events happening in that case is just the product of the two probabilities. So in other words, we kind of observe that if A and B are independent events, then the probability of A and B is just the probability of A times the probability of B. But notice that I haven't actually called this thing a law, and I haven't proved it as a theorem. I'm just, at the moment, stating this as something which seems like a reasonable observation, given a reasonable definition of what independence of events might be.